Okay, welcome everyone to the, I believe, fourth brown bag seminar of the fall semester. Thank you for coming, those who are here in the room and those who are still online. Thanks for all coming. We're going to have two speakers today. And as usual, if you have any questions during the presentation, if you are online, just go ahead and chat them in and I will ask them at the end of the presentation. If you're in the room, please hold your questions until the end of when that speaker's finished, and then we'll ask questions at the end of each speaker's time. Okay? All right, so our first speaker is Ben Breer. He's an undergraduate student here at Georgia Tech. I guess you wouldn't be a student anywhere else, would you? Silly to be here right now. He's double majoring in aerospace and physics, one of those very common double majors. And he's been working in the combustion lab for about two and a half years now, working for Professor Lewin, and he'll talk about his research today. But he's also been an intern at Aerojet Rocketdyne, working on 3D printed propulsion components, so it brings some interesting experience there. And more importantly, he's the chief engineer of the Yellow Jacket space program on the liquid rocket. So, and I believe your plan is to stay for graduate school.
Yes, that's the plan.
He likes it here.
Pretty good. Yeah.
All right. Well, let's all thank Ben, and we'll listen for his presentation.
All right. So I will be presenting today on mode identification and prediction of thermoacoustic instabilities. It's a very interesting topic. It's pretty up and coming. It's been around for a while, but there are a lot of new methods out there that are being applied in this field. So today I'm going to talk about the work that I've done at the combustion lab related to this. So yeah, I've been at the combustion lab for about 2 years now. I've worked on 3 big projects. Today I'm really only going to be touching on 2 of them, and predominantly the first one, which is modeling transverse mode shapes. And I'll discuss what that means. And then I'm working on instability mode prediction, so taking operating conditions, being able to predict instability modes based off those conditions. And then recently, I've taken on a new project, which is trying to look at NOx emissions from hydrogen and methane fuel blends. This is like a very important topic because currently emission standards don't adequately capture like true NOx production and its effects in the environment. So again, briefly today, I'll just be walking through a small background on thermoacoustics, what you need to know so that you're not completely lost in my presentation, going through simultaneous mode identification, mode prediction, and then I'll discuss a little bit on the current work that I'm doing, and then we'll have some time for Q&A. So I always love to start off whenever I explain thermoacoustic instabilities with this diagram, this GIF, which was kindly provided by Jin-Won Kim. What you're looking at is a transverse mode, and what you're really looking at is the velocity, the flow plotted against the mean flow. So that's why you're seeing that oscillatory behavior there. The main problem here is that lean premixed combustors, they are prone to having high frequency transverse instabilities. And this can essentially act as a high cycle fatigue, which can destroy your hardware. This is a real issue. Companies like Mitsubishi Heavy Industries come to the combustion lab here at Tech to solve this problem. And that's exactly what this project was about. The primary goal was to identify the transverse acoustic mode shapes. And so really what that means is trying to reconstruct the acoustic or thermoacoustic profile inside a combustion chamber so that we can better understand it and then hopefully in the future predict the operating conditions that will not lead to those instabilities. So we apply a variety of methods. Really, it's guessing and checking by varying combustion parameters, primarily a pilot ratio and equivalence ratio, which I'll touch on, to purposefully generate these instabilities. We want to generate instabilities so that we can rule out those operating conditions. And then really the reconstruction process of this acoustic profile happens in 2 directions, the azimuthal direction and the axial direction. And I'll go a little bit more in depth about that. So this is the rig that I worked on, rig, Mitsubishi Heavy Industries, pictured in the upper right. And it's a can-annular combustor rig. So basically there are multiple cans, 8 cans mounted concentrically with a pilot nozzle. And this is a lean premixed methane air rig. So we mix the methane and air upstream of the combustor, and it's a lean system. So we're not trying to waste a lot of fuel. There are 8 outer nozzles, as I said, and then we control the fuel flow by basically tuning the pilot ratio, which you can see is just the mass flow through the center nozzle in proportion to the sum of the pilot mass flow rate with one of the outer nozzle mass flow rates. We also have the equivalence ratio, which is just your ratio of your actual fuel-air proportion to the stoichiometric. So we vary these two parameters in our experiments. It's worth noting that we have some fixed parameters. So for each of our experiment runs, we fix our preheat temperature and our inlet pressure. We will adjust these for sets of experiments, but typically when we're varying the pilot and equivalence ratio, we try to keep all the other knobs constant. It's not very prudent to turn multiple knobs at once because it's hard to answer a question. This is just a diagram of the combustor. So essentially air goes along the walls of the combustor. That's actually heating it up, and then because it's drawing heat from the combustor walls, then it's injected. So this project is about trying to identify mode shapes, and it's worth noting that there are two primary modes for a can-annular combustor for this rig, which is a spinning mode and a standing mode. And a spinning mode is exactly what it sounds like. You see oscillatory behavior going in one direction, counterclockwise or clockwise. The standing mode is when you have competing modes. So the counterclockwise and clockwise spinning modes are competing against each other. They're feeding and destroying off of each other. So there's some destructive interference there, and you just result in a fixed nodal line position. So you're not having any oscillatory behavior, you're just standing. And the primary question that we're trying to answer is, how do we determine the mode shape? Like, how do we back out the acoustic profile? And what we do is we use raw pressure data, temporal pressure data, and we vary the pilot and equivalence ratio, get different pressure measurements, and then we try to back out things like the nodal line position and actual like coefficients that correspond to these modes. And I'll explain a little bit what I mean by coefficients. First, I just want to outline some assumptions. This is assumed to be a perfectly cylindrical geometry, so this is how we treat our combustor. We say that there's no mean flow because we have a low Mach number. This is one of those assumptions that we can remove later on. I just wanted to note it here because this experimental data was compared to CFD performed in ComSol multiphysics, which had this assumption. And then we assume uniform density and temperature post-flame. Our primary methodology, I was really trying to think about the best way to explain it because I figured it was really like a multi-step process, and it kind of boils down to these 5 steps. We take the raw pressure data, which is measured from high temperature pressure transducers mounted at different points in the combustor. We take that raw data and we break it up into 1 second intervals. And we do it in 1 second intervals because in the combustion world, as you will find if you go into it, 1 second is a lot of time. So we take these 1 second intervals, we perform a fast Fourier transform to get it into a time signal, or going from a time signal to a frequency domain. What that allows us to do is we can plot the amplitude, the pressure amplitude, as a function of frequency. And you might be wondering why we do that. We do that because we want to see where there are amplitude peaks, and we want to find the corresponding frequency. Because instability modes is another way of saying, at what frequency do I have this unstable process? We then apply a bandpass filter, and the reason why we apply a bandpass filter to our frequency space, our amplitude frequency space, is because for can-annular combustors, the frequencies of 2 competing modes are very closely spaced because they're such high frequency, and honestly, the geometry of the rig is going to yield closely spaced modes. So we apply a bandpass filter to narrow down the 2 peaks, really identify them as separate modes instead of just one homogeneous single node. And then we perform a data fit, and we basically solve the 3D wave equation in our geometry. And that's how we back out these coefficients. The pressure data that we have, this is just actually a snapshot of all the data that we've had. We ran this rig multiple times. We take this data, we feed it into a program I wrote that's just written in MATLAB, and essentially it goes from raw pressure data to telling you what acoustic mode do I have and what is its shape. And so I want to walk through the process just a little bit. So we start with a time signal of pressure, and you can plot it as a function of time, because that's what the data is measured in. We have multiple different sensors at different azimuthal locations. So we just plot all of them at first, and then we can look at each sensor's measurement. And so we basically apply the bandpass filter after converting to the frequency domain. And by applying the bandpass filter, we're able to identify the peak frequencies. These are the frequencies at which we have unstable conditions. And then we convert it to an analytical signal. And this we do using the Hilbert transformation. And this is going to allow us to actually numerically solve our 3D wave equation. And so this is the fit to the 3D wave equation in a cylindrical geometry. So essentially you have coefficients, real valued magnitudes that are multiplied by exponential functions. And there is a azimuthal position for the sensor, so that's our theta. That's going to change for what sensor we're using. And then there's a phi, which is going to be the phase of our wave equation. Because we have multiple sensors, we had 4, technically we had 5, but 4 were really working. We basically applied all 4 sensors together, and then you can build a matrix or a system of equations for each pressure measurement. And then you can use a least squares method to back out what, based on the azimuthal position, what your spin ratio is. And really what that process is doing is it's basically just trying to resolve the coefficients. Those are those a hat plus and a hat minuses. And the spin ratio, if you think about it, going one direction versus the other, you can think about it as the ratio of a difference of the 2 coefficients over their sum. And based on the value of the spin ratio, you're going to be able to determine whether or not it's clockwise or counterclockwise. So it'll be +1 if it's clockwise, or -1 if it's counterclockwise, depending on how you define your direction, or 0 if it's standing, when they compete against each other and your numerator approaches 0. And so from this program, we start spitting out pretty useful plots. One of the motivating questions was, how do our modes develop over time? Like, A, what is the mode shape? But B, how do these modes develop over time? And so we can look at the time evolution of the spin ratio and the time evolution of other parameters, but primarily spin ratio. And then we can plot spin ratio versus pilot ratio, trying to establish a relationship between how we're throttling the combustor and the resulting modes that we get. It's worth noting that we can also calculate the nodal line position. What this is if you basically picture a propeller on a plane, but it's only like 2 blades and they're across from each other, so you have a line. This propeller is going to be spinning in the combustor, and that's your nodal line. So the nodal line is where we have a lot of destructive interference, but the antinodal line, which is orthogonal to this line, is going to be where we have these modes. So if you can find the nodal line position, which is going to evolve over time, then you can find the evolution or the temporal evolution of your instability modes. And so the main takeaways from this project is that we can develop like this all-in-one program that takes raw pressure measurements and computes the actual mode shapes. It's also worth noting that like there is a identical process for the transverse mode, or sorry, the axial mode, and that process basically involves fitting it to, instead of a cylindrical wave equation in 3 dimensions, it's a left-handed and right-handed waves because of that axial motion that you have for the instability mode. The purpose, now that we have this program, is to run as many experiments as possible, feed the data into this program, back out the acoustic modes, build a better understanding of how these modes form and how they develop over time. And then hopefully we can start to determine operating conditions that will not result in these instabilities. Because if you can find all the times and operating conditions that your combustor is possibly going to experience hardware fatigue, then you can reduce those operating conditions in your power plant. So the next stage, which is really transitioning to the second project that I worked on, is predicting instability modes. And it's a different mindset than just modeling. When you're modeling something, specifically these instability modes, you were taking known data, you were feeding it into a program, you were number crunching, and then you were backing out what those modes were. When you were predicting, you were doing an iterative process of stepping forward, making an educated guess, essentially, finding out that you're wrong, and then backing up and saying, okay, let me guess again, step forward, how wrong am I now? Am I more wrong or am I less wrong? And that's sort of the process of how we predict instability modes right now. It's worth noting also that when you start predicting modes, you want to be able to capture effects like modes feeding off of each other. You also want to capture the fact that you're going to have unsteady heat release rate. And if you truly want to model a realistic process, you can pull from distributions. And then you need to start using some stochastic mechanics to solve basically the instability modes based off an unsteady heat release. And so it seems very complicated, but there are really 2 main approaches that we've considered so far in the group I've been in. The first approach is you treat it as a control block diagram. I, at first, did not gravitate towards this approach. I love thermofluids, but this approach, I think, distinctly models what we're trying to do. QS is the heat release, and this is treated as like an input to your combustor system. Then you have the nonlinear dynamics, the nonlinear acoustic dynamics. That's captured by F. And that right there is our feedback loop. So it's going to be driving more instabilities. You can't just have an input and then consider the output. You need to consider the output and feed it back in so you can keep adjusting your model. You then have G, which is, or really I should refer to this all as H, which is our like acoustic dynamic system. And that's composed of G, which is really going to be modeling the effect of the acoustic dynamics, the passive acoustic dynamics. And then you have F, which is the acoustic dynamics from the flame. So there's a couple things going on. You have a flame that's generating heat. That heat is being released in an unsteady manner. And then you have the ambient noise and the resulting acoustic dynamics from a flame. So we try to separate it out to model it appropriately. And really this is treating it as a nonlinear and nonlinear and linear system combined together. And so if you look at the control analysis, you can boil down the equation that describes the development of your acoustic modes. And before I go in more to that, I want to touch on the second approach, which I still find a little bit more useful because it goes back to the actual thermodynamics and fluid mechanics happening. If you start with your state variables and you add an unsteady time-dependent term, and then you apply it to a wave equation, which is basically our way of evolving these states over time, and you use lots and lots of math, I cannot stress that enough, then you are able to boil down the modes and how they develop over time. And so you get to the same place from these two different approaches. There are some differences, but in the end, it's essentially the same. And I still gravitate towards this because I think it's a little bit more tangible. But essentially, yeah, you're using the wave equation. You impose your acoustic velocity, which is essentially a boundary condition on the inside of your combustor. And then you treat the unsteady heat release rate as the sum of a deterministic, something that you can do on pencil and paper, with something that's stochastic, where you need to pull from a distribution. And that distribution, you can actually choose from different sets, and that will influence your results. The more math, the methods that we use is basically converting the eigenmode into a phase amplitude space. And what this does is it allows us to eventually back out our combustion parameters. So based off of your acoustic modes, which is basically an eigenmode problem, you can figure out the phase and amplitude as a function of those eigenmodes. Doing some more math and some really, really fancy approximations, you can develop the functional form of the amplitude as a result of these instabilities. This is very important because this is where we now have crunched some numbers, we've taken a step forward, and now we're asking ourselves, how close are we? And that's exactly what we're doing by this curve fitting process. So we have the functional form of the amplitude. We can generate a data set by numerically solving these eigenmodes. And then we throw them together and we try to find the coefficients from this functional form that fit that data. If we find those coefficients, we then want to ask ourselves, are those coefficients different or the same as the original parameters that I had from my data set? Spoiler alert, the answer is usually they're not the same, and you want them to be the same. So then you say, okay, I'm going to do this process again and again and again. And this involves really thinking outside the box. Like for instance, in these two plots here, you can see that we've curve fit over the entire range of amplitudes. But in this region, it's highly, highly nonlinear. It's extremely not well put together. So we cut down the amplitude range so that we can get a better set of data to curve fit to. And sure enough, our parameters were closer to the ones that we had set when we generated the data set originally. So the current work in this project, there's a lot still to be done. I've been on the predicting side of instabilities for this project for about a little over a year now. And it's taken a long time for me to grasp just the math behind it and also just the thermofluids. The current work is associated with building up these Python and MATLAB programs so that we can better predict instabilities using more data sets. And so trying to create an iterative process that can handle hundreds of data sets and then also get into a little bit of machine learning where you can back out parameters and do better educational guessing. I want to thank Professor Lewin, David Wu, Jinwon Kim, Tony John, and all the other people at the Combustion Lab that have made my time there for the last 2+ years amazing, and I really hope to stay there for graduate school. Thank you so much.
Okay, time for questions.
Yes, Ethan. So that's a good question. We have high frequency, high temperature pressure transducers. The first set of data, right here, the first set of data that we grabbed from this rig, we used, they were fairly low frequency transducers compared to this project. We're talking like 1 kilohertz. And we were not able to adequately capture the effects of the instabilities, but we sample our data at 20 kilohertz. And that enables us to remove any effects of aliasing because our instability modes, if we go to this spot right here, and if I zoomed in a little bit, this is 1600 hertz. So we prevent the aliasing effect by sampling it at such high frequencies, around 20 kilohertz. Yes?
Yeah, I have a question. One of the things you're trying to do is, for example, compare your predicted results and your actual results. You talk at all about how, when you go through this process of interpreting the data from the pressure transducers, what your uncertainties are like when you do your bandpass filter, how much that affects the signal, your uncertainties, and all these things, like you change numbers a little bit. How much do some of those coefficients change? Okay.
Yes. So that was one of the biggest aspects of the beginning of this project. The bandpass filter that we apply here was an extremely sensitive step. Our bandpass frequency, so this del F, basically the frequency that we're bandpass filtering, we had this at like 5 different frequencies, and it took us about a couple weeks to find the right range of frequencies that would result in our like modes not changing that much. What I mean by that is we started off with 200 hertz without seeing these amplitude frequency plots. And as a result, we were capturing this smaller peak because it's between 1600 and 17 hertz. So it took a lot of trial and error to determine that our bandpass filter frequency needs to be on the order of around 60 hertz so that we're able to isolate the peak frequency. And we then had to test if that frequency was sufficient by going through all of our data. And there were a couple cases where 60 hertz was still too large of a bandpass filter frequency. So we were actually starting to capture the second peak. So one of the, I would refer to it as like an open-ended like problem is how do we optimize our bandpass filter frequency? Because it changed a lot from one experiment to the next.
So to follow that up, I presume what you're using the bandpass filter for is to actually somewhat integrate the signal over some frequency, right?
Yes.
That's what you're really doing.
It's isolating and integrating.
Well, your data is more resolved than 60 hertz.
Yes.
So you're just trying to essentially average over that some number.
Correct. Yeah.
So what prevented you from making it narrow?
The only thing that really prevented us from making it narrower was like how narrow do we go? We didn't really have an answer for that. And yeah, that's one of the things that would keep me up at night is like, if I keep decreasing this bandpass filter frequency, how much are my results going to change? And how much can I trust the results from these acoustic mode shapes if, and this one step, it's so sensitive to how I bandpass filter? We discovered, and this is just based off of looking at hundreds of amplitude frequency plots, that any bandpass filter frequency below 10 hertz was not able to capture the entire peak of one mode. So we established empirically some lower bound for our bandpass filter frequency, but it was empirically. So I still think one of the improvements for this model, or for this program, could be some way to optimize the bandpass filter frequency. Somehow have the program ask itself, is this bandpass filter frequency going to properly integrate at this peak frequency, capture the mode, but also if I decrease it, is it going to change the results by a lot?
Other questions? So I'll go ahead and ask one more.
Mm-hmm.
So when you did the analysis, right, looking at trying to look at different noises, did you give the choice of noise distributions some idea of, I guess, the noise characteristics you're picking? Did that make a big difference in the results?
So for the predicting modes, I have to say I have not played around with the noise distributions that much to be able to see an effect. We have been using like a Gaussian noise distribution, but there's also like color Gaussian distributions that you can pull from. One of the questions that I know Tony is trying to answer is how does that noise distribution impact the resulting modes? There's definitely something to be seen there, but I personally have not been able to discover that yet.
All right, well, let's thank our speaker again. Switch over here. Just a second. If you are still broadcasting that. Okay, our second speaker today is also an undergraduate student, obviously here at Georgia Tech. And instead of double majoring, you're minoring in computer science with a focus on intelligence. I'm hoping all of the people in the audience are focused on intelligence too. You'll be graduating this semester, I understand, and you're already planning on coming to the master's degree here in spring, so sticking around, good stuff. You're working for Professor Lightsey.
Yeah,
that's correct. So we'll be talking about the research you've been doing as part of the BSMS program with Professor Lightsey. So let's all thank our second speaker and look forward to a great presentation.
How's it going, y'all? As Dr. Seisman introduced, my name is Keshav, and I will be presenting on the Inhibit Switch design that we had for the GT2 CubeSat mission, which I'll explain more details on that in the presentation. So a little overview of my time specifically in this lab. I joined the GT2 structures team this spring. I got introduced to the lab, got introduced to what this project is about, and started working on our Inhibit Switch design. Took a break in between to do my internship over the summer, and then I came back in the fall to work on updating our Inhibit Switch design, which I'll discuss the changes that happened later on, and then making additional changes to our CAD model or chassis based on different requirements and adjustments we wanted to make, and any other things that are needed from us for the structure side. So a little background into what GT2 is. So GT2 is part of a bigger program called GTX. And GTX is essentially the development of 4 1U CubeSats. 1U is in 10 centimeter by 10 centimeter by 10 centimeter. And 4 1U CubeSats to be developed annually. As you can guess by the name GT2, this is the second iteration. GT1 was worked on last year, some with a little break in between for COVID-19. And the GTX CubeSats are mainly designed by undergraduate students. We work on it from design to assembly to operation. And one good thing about it's really cool to have a bunch of undergraduate students working on a project, but another issue is there's a big overhaul with undergraduate students leaving. And so an important thing is having really proper documentation so that new people coming to the lab have an understanding of design decisions that were made by people that are no longer there. So what we're working on right now is GT2. The goal is to try and improve on GT1 design based on lessons learned and issues that happened when that CubeSat was being designed. So a little explanation of what I mean by inhibit switches. So a more common name is known as deployment or separation switches. The reason we use the name inhibit is essentially what its purpose is. It's inhibiting the flow of electricity in our circuit, so to make sure that our battery does not power our components while we're trying to launch. This is extremely important. If we have our power running when we don't expect it to. Certain components could malfunction, and it could lead to damage to those components or to our CubeSat in general. And then another issue that could arise if power is continuing to run while we're launching is our operational life would be decreased. Our battery has enough power to supply our components, and if we use some of that battery life while we're actually launching when we don't actually need to run anything, then we just decrease the amount of time we can do something useful up after launching. So the way these inhibit switches work is when they're depressed, they act as a open switch in our circuitry. So when it's open, of course, no power is going to run through, and none of the electrical components are going to work. And then these switches are depressed because they're loaded into a pod, which I'll describe later on. And after they're loaded in a pod, they get pressed down. And then when they get deployed from the pod, these switches then get actuated. And then the circuits are then closed, and the electricity is able to flow through, and the components are able to properly function. So as I mentioned, these CubeSats are put into pods. The pod that we're using for this mission is the JSSOD, supplied by JAXA. It's a orbital deployer for small satellites. The picture to the far right, I guess far left, it's over here. This one right here is the JSSOD that we're going to be utilizing. As you can see, there's space to fit multiple CubeSats in there. There's a total of 3 1U CubeSats that we can properly fit in. And the way that these CubeSats get launched is that they get all put in there, they get launched up from the ISS, and then from the ISS, this JSSOD is sent out. And then there's a spring, as you can kind of see here, that kind of pushes the CubeSats out, and then they deploy from there and then form their normal activations. Typically, looking at the inhibit switch design, there's 2 main locations that generally these inhibit switches are located. They can be on what we call the -Z face. If you have the CubeSat looking straight up, it's going to be at the top. And then remember, loading it up into this pod right here, it's going to be the ones closer to the face of the CubeSat closer to the spring side. Usually these are push-button switches, and they will lie up against the +Z face or the bottom of another CubeSat that's in the row or in the pod. The other location that these switches could be located is along the rails, so along the sides of the CubeSat. And these are usually lever switches or roller switches or simulated roller switches, which are like lever switches with a curve on them. And they usually are depressed against the walls of the pod instead of other CubeSats. So based on the deployer, there's an interesting decision on the number of inhibit switches that you want to use. Some deployers, like for Cal Poly's P-Pod, only 1 inhibit switch is required, but they recommend 2. But for other deployers, like for the ISS, the CubeSats need at least 3 deployment switches. This is to have like double point failure. And it's an interesting decision, like if you only have 1 inhibit switch, an issue that could arise is as you're launching, due to rattling, your switch could not be depressed anymore, and then all of a sudden your circuit is closed and your components run unlike what you would intend. So having multiple switches could mean that when you have, like, let's say 2 switches in theory in your circuit, if one of them is not depressed but the other one is, then your circuit still won't be able to activate. So it provides protection against one of your switches not functioning as intended. However, the flip side to that is if you launch your CubeSat and one of your switches stays depressed, then your CubeSat just won't work, and it's just a box sitting out there. So it's an interesting debate to see what is the balance you want to have between how many deployment switches you use to balance out not having a inhibit switch fail to depress, and also having a switch actually actuate. So not having your CubeSat operate when you don't want it to, but also having your CubeSat operate when you actually need it to. So ideally you want more than 1 switch to avoid any single point failure. There's a bias to having more deployment switches because there's a higher chance of when you're launching for rattling to cause a switch to be undepressed than for a switch to stay depressed after you launch. So before getting into our design decisions for our inhibit switches, I just want to go over some of the requirements that we really had. So some of the requirements we had for the CubeSat real quick. Some of them are pretty obvious, like making sure the deployment switches, preventing activation. and additionally making sure the materials are appropriate to prevent any outgassing. But the main requirements that played an impact in our decision making were regarding how far the CubeSat, how far the switches could be off the surface of the CubeSat. So the main impacting requirement was requiring the stroke of the switch to be around less than 2 millimeters off the surface. So this is the free position of the switch. And this creates a constraint on how deep our switches have to sit in our structure, which is a bit of a concern because we also have a bunch of other components in our CubeSat. And being a 1U CubeSat, there's not that much space to work with. So if our switch is very bulky and large, it'll start trying to interact, or not necessarily interact, but get into the space where other components would want to be sitting within our CubeSat. So to cover up what GT1 did, they had a push-button switch, and they picked this specific one because it met the material requirements to be launched into space, and it was small enough to actually fit properly within our CubeSat, and it fit within the budget of what we needed for the mission. However, there were some issues that arose with trying to integrate this switch into GT1. The good news is a lot of that was due to human error and machining error and improper design rather than the Inhibit Switch reliability itself. Some of the issues that arose was in the design, the hole to actually put the Inhibit Switch in was designed a little too small so that when we got the Inhibit Switch, it wasn't able to fit in, so we had to clear up some space, properly fit the Inhibit in. Other issues were during machining, the angle of the hole was a little bit off. And then lastly, there was when we actually integrated the switch into the -Z plate, the switch was laid a little too high than anticipated. So then when we perform vibe testing, and a quick aside, vibe testing is essentially providing vibration towards our CubeSat to give it a test condition to what it would experience, like, for example, when it's launching, to see if there's any glaring concerns that arise, and see if there's anything we need to fix. So when vibe testing was performed, the plungers of the switches rattled a bunch, and they rattled so much that the switches actually broke. So because of the challenges that happened because of integrating these switches into our CubeSat for GT1, there was a desire to switch to rail limiting switches. As you remember, I brought up there was the push button switches on the -Z plate and then the rail limiting switches on the walls of the CubeSat. So the rail limiting switches are beneficial because, one, they avoid major rattling concerns that would happen during vibe testing. Because if you remember, the push button switches would lay up against another CubeSat, while the rail limiting switches would lay up right against the walls of the JSSOD, and there's less chance of vibrations happening to when laying against the walls than while up against another CubeSat. Additionally, because of the existence of separation springs on the -Z wall of our CubeSat, we only had 2 push button switches, so that was a single point tolerance. However, by placing switches on the walls of the CubeSat, we could actually fit way more switches, so we could have more fault tolerance, and our goal was to have around 4 total switches. We chose lever switches, because of how it would properly fit into laying up against the wall of the JSSOD, and also because the lever switches were a bit more sturdier than the old push button switches, so we would have less concerns about it potentially breaking. So the Inhibit switches that we chose was the IX1-T with a JX41 lever arm. There are 2 separate components. The lever arm is fastened on to the switch. We chose this specific one because it met, again, requirements that we needed. And additionally, it was used with success during testing on the CXBN2 CubeSat developed by Moorhead State. It could handle very high electrical load, and it was very reliable. I had 0 issues during testing, so we decided it's pretty reliable and other people use it. Why not go for it? The benefit of having the lever arm being separate from the switch itself allowed us so that we could actually modify it and design it for an appropriate way to actually fit our requirement of, again, being under 2 millimeters. So as I was saying, there isn't that much space to fit our switch into. The JX40, which was actually what was used with the CXBN2, had its lever arm going from this side up over here. And in order to leave enough space between this switch and this lever, this means this lever arm would have been at a higher position than this lever arm would have been. And that position of the lever arm was going to be past our 2 millimeter requirement. So having the ability to separate our switch from our lever arm allowed us to have a lever arm our free position of our switch that was less than the other design, and therefore actually probably fit it into our CubeSat. So going into where specifically we placed these switches, we had them on 3 of the 4 rails of the CubeSat. This is mostly because of the avionics stack that we have in between. The standoffs were right by the edge on the minus X plate, and there was not any really good room to actually place these switches on there. So yeah, we put the switches in there, but however, while we were designing it, and as the design changed slowly with different groups adding their CAD models in specifically, we noticed there were some more issues with the rail inhibits. One concern was regarding over travel. There was only a 0.1 millimeter gap in between the 1.9 millimeters of the free position of the switches versus the 2 millimeter requirement. And there was a concern of if there was human error while trying to put the push button switches in to the CubeSat, there was a concern of maybe putting these switches a little too high as well. And those issues with placement and a fear of 0.1 millimeters, which is very, very small, of a human error, had a concern. So if we put the switches a little bit more deeper into the structure to avoid, to leave a little bit more tolerance between the minus 2 millimeter requirement, some of the switches also wouldn't be able to fit into the structure, and we could only actually fit in 2 specific switches. And that would reduce the amount of fault tolerance that we had and bring it back to a single point fault tolerance system, which isn't too much better than the single point fault tolerance system we had for the inhibit switches on the minus D plate. Additionally, there was a concern of having an increased mass to the CubeSat, and then later in the process, we got a new requirement that the switch needed a rolling or simulated rolling switch instead of just a pure lever switch. So we decided instead of making a rapid search to try and find a new switch that worked, additionally with trying to fit in these bulky inhibits and trying to alter design too much, we would switch back to the old inhibit switch design, partially because it met the requirements and the switches in the lab. But we made some adjustments to the structure. We left a bit more space for the hole so the inhibit switches could properly sit within. And we kept in mind to updating our integration procedures so that we would be able to properly fit our inhibit switches into the holes that they were provided. And then the last changes we made to our structure is when we got a new requirement later on in the process that the mission required 3 switches for double fault tolerance. So we replaced one of the separation springs with an inhibit switch. And at that point, we realized that the total force of the inhibit switches when they release was actually equal to the amount of separation force that we needed to deploy from the other CubeSats. So we decided to eliminate the separation spring that we had from our structure just to avoid any unnecessary complexity and just get rid of something we actually don't really need. Looking to the future, we would potentially try to find push button switches that are a bit more sturdier along the process and search earlier. Part of the issues why we stuck with the same push button switches that we had originally was because very late into the design process, we were told that the lever switches that we had wouldn't work. So instead of trying to make a rapid search to find a push button switch that worked and make adjustments to those push button switches, we just decided to stick with what we had that we knew where the faults were and make adjustments instead to our procedure instead of the design itself. Another thing we could do is potentially try to find any smaller lever switches that could work. Now that we have a solid understanding of the issues of fitting these lever switches into our design, we could now have a better understanding of what the requirements are for lever switches in our CAD model and potentially find ones that better work. And the last thing we could do is a bit ambitious, but we could potentially look into manufacturing our own switch in-house to meet specific needs. This would be good as it would prevent any major issues that we had with placing the switches into the structure in terms of sizing and space, but also leads to a lot of human error and issues in the switches just not being that reliable as switches we get from other suppliers. So to cover up the last couple of things, I just want to go over the last couple of steps that GT2 is going through this fall. Looking at the structures team, right now we are currently finishing up writing any documentation to get reviewed by Spaceflight, who is our end-to-end launch deployer. After that, we will manufacture all our components that we need, order any necessary parts, and then perform a final structural fit-up of our CubeSat. And then lastly, after that, for GT2 in general, getting a complete development of all our components from all our different subsystems such as AVI, flight software, structures, and then completing a full system fit-up with power, and then try and perform our final integration by the end of the semester before we perform testing in the spring before our final delivery date of, I believe it's April 25th. So that's my presentation. Any questions? Yeah.
At some point, separation forces.
Mhm.
Was that like, in what condition was that true? Is that just confident? By removing the spring, that removes a failsafe.
Yeah, so it was in the nominal condition, but there wasn't any major concern that we had that the switches wouldn't be able to release at the same level as the spring based on previous testing we had done. That's again going to be a thing we will probably bring up with when we perform a bit more analysis into things, because that was a change we just recently made. Yep.
What portion of the entire CubeSat's mass for this?
That's a good question. I am not 100% sure, but it is not a significant amount. The push button switches we have are extremely, extremely light, to the point I'd say it's probably a negligible amount compared to what the overall mass of the spacecraft is. Yep.
So I was interested at the beginning when you talked about the opposite failure,
Mhm.
that one bad switch will prevent you from operation. Is there anything that anyone or you've looked at to ameliorate that problem that we have? Switches, that one will fail to close the circuit?
Yeah, so there are some people that have tried to look at design the circuit in a different way. Like if you have three switches, where you could design it where if two go off, then, or if two release and one stays depressed, then through the way you route your circuit that the your CubeSat will still be able to operate. I haven't done a full investigation to the specific circuitry on how people have accomplished that, but I have read papers on people trying to decide how they could alter their circuit, their inhibit circuit, to make sure that it still functions even if one of them stays depressed.
Are there the requirements that this switches be unpowered? In other words, you can't have a separate small power source operating at that time to do something more digital or something else, so that you could look at, do two switches agree? Standard other way of doing things. I have two things. If they don't agree, then I'm worried. If they agree, I know they're right.
Well, then the point that comes up with that is they both fail.
They both fail, you're in trouble, but you're already in trouble.
Yeah. Yeah. I guess that would kind of fit in with the thing if you have three inhibit switches, which is the most common requirement nowadays days, where if two succeed and one fail, or one succeed and two fail, that would kind of match up with what you need. Because if all three fail, you're messed up. If all three succeed, you're all good. But if two work and one doesn't, that's the other operating condition. So having your circuitry designed in that way where it allows for two to succeed and one to fail would be the way to try and handle that.
But are you allowed to have power flowing through any part of the circuit, have a sub-control circuit, or you have to have no power flowing while you're in launch? You have a separate small battery, very, very small battery that could have power flowing to something else besides just manual open and close circuit.
I don't believe that there's that they want power to be running simply because of the risk that it could have to other CubeSats. Usually when these deployers are looking into fitting these requirements, their main concern is not whether your thing works, like after it gets launched. They're like, we just don't want anything to get blown up on our side. So I don't recall them allowing any power to be running while you're trying to launch.
So the requirement says no power as opposed to no power above this level. Or no.
Yeah. Yeah.
Other question? Could you go back and explain the reason you got rid of the sidewall switches? Are you saying it's just a small problem at the last minute, or you just say that you think the end switches are much better in general than the side switches?
So the side switches are better in terms of their reliability and in terms of potentially having less issues in vibrations. Our main concern was the size of them and trying to actually probably fit them in. It was mostly because we were nervous about human error leading to a lot of issues, and because of how tight the spacing was, we were concerned whether dealing with these sidewall switches, if we placed them improperly during integration with such small spacings allowed for the switches, that more issues could arise.
And would that be overcome better by changing the lever that you're using or by changing the depression switch it hits?
So I think probably the best way to do it, I mean, would be to decrease the lever. The switch itself isn't too much of a concern, but the length of the lever switch, and we looked at trying to machine down the length of the lever switch as well. I think decreasing the height of the lever switch would probably be the best. Also, another thing would be just decreasing the like the height of the switch is actually probably the biggest concern that we had. If that was decreased, it would probably be better. But because of how like high the distance between right here to right down here is, it starts interacting with our standoffs.
Is that height set by the electronics of that switch going up or down, or just by the structure of that thing that they built?
The height of this entire thing, you're saying?
Box.
Of that box?
That's primarily just a structural thing. There's nothing inside.
No, there's items inside, but again, it's possible that there's other switches out there that are either like longer and fit everything inside, or not as high. So that's what we would ideally try before.
Any questions? Okay, let's thank our speaker again. I hope everyone will attend next week. Presentation. Until then, have a great weekend, everybody.